Good evening, everyone. We are in the summary session of this NPTEL course, Network Analysis. I am Teja Golla, a fourth-year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. So till now, we have discussed about all the entire weeks, and I have conducted 12 problem-solving session for the 12 weeks of this NPTEL course. And this will be a summary session where I will be summarizing what all we have discussed in the 12 weeks. So let me quickly summarize. You are able to see my screen, right, Jnanendra?
Yes, sir.
Okay. So do you have any doubts, or should I summarize what all we have discussed in these 12 weeks?
Sir, I will ask on last if I have doubt any.
Okay. So let me just quickly summarize. I'll just touch upon what we have discussed. So if you have any doubt at any time, any point of time, you can ask. We are in the week one, and week one was about introduction to network, circuit element, and sources. So we have started with the basic mesh analysis. So we have considered one circuit where we have applied mesh analysis, and then we have seen how to write this equation. And because there are three meshes, we have also discussed mesh is not any closed loop. Mesh is any closed loop within which a mesh does not exist. So this is considered as a mesh. And then we have also discussed about super mesh. And this super mesh happens when two meshes share an ideal current source. And when such thing happen, we'll consider the outer mesh and we'll apply something called super mesh analysis. And then we'll get different equations to solve for the different unknowns. Then we have solved one problem quickly. And this is normal mesh, not a super mesh. Then we have gone to nodal analysis, and then we have discussed node is any intersection of two or more branches. And then we have seen how to get these equations, and we have discussed these equations thoroughly. So here we have three equations, three unknowns. Similar to super mesh, there is also called a super node when this happens when two nodes are sharing one ideal voltage source. And in such case, we'll combine this as a single node and we'll call it super node. And we have seen how to solve such problems. Then we have solved a couple of problems. In the first problem, we have a super mesh. So we have considered the outer mesh, and then we have solved for whatever they have asked in the question. Then similarly, one important thing that we have discussed was delivering power and absorbing power. So I have given the convention. When something is delivering power, it gives current. And if something is consuming power, it draws current. Similarly, same with the voltage source or with the current source. But a resistor can only consume power. It cannot supply power because it's a passive element and it always consumes power. So this is what we have discussed in the week one. After that, we have discussed about a deeper look into energy storing elements, which are the inductor as well as capacitors. So here we have discussed about the circuit elements, mainly resistor, capacitor, inductor. And we have seen what is the voltage current relationship between the resistor, capacitor, as well as inductor. And then we have seen that in the case of resistor, voltage and current can change instantaneously, whereas in the capacitor and inductor, there are some restrictions because capacitor voltage cannot change instantaneously, because in that case, the current will be infinite. Similarly, inductor current cannot change instantaneously because in that case, voltage will be infinite. And then we have also discussed about uh, which are energy storing elements and which are energy dissipating elements. Resistor is energy dissipating element. Capacitor and inductor are energy storing elements because it has memory elements. Also, resistor is memoryless element because it depends upon the instantaneous voltage or current. Whereas here we'll have integral term, so it has memory. And then we have seen why it cannot change instantaneously, because in that case there will be infinite impulse and that will damage whatever devices that are connected. So that's why it is it cannot change instantaneously. Then we have seen the inductor current equation, and it has some initial condition. And similarly, capacitor, here the initial condition will be on the voltage. So whatever equation that we are getting for capacitor as a voltage, we'll get the same as a current in the case of inductor. So everything remains same. Then we have solved a couple of problems. I will not go in detail of the problems that we have discussed, but I'll just briefly summarize what we have discussed. So basically, here they are connecting one inductor and they're asking how much time is required for the inductor current to reach 8 amperes. So basically, what we have done is we have applied what all we have learned in the week one, which is mesh analysis and nodal analysis, and convert it into a differential equation, and then apply integrals, and then solve by classical method, and then we got as a function of time, and then whatever they are asking, we are substituting the time or value of the current to get whatever they are asking for. And then they have also asked for energy. Energy is nothing but integral of power. Power is nothing but voltage into current. So we have substituted current and voltage. And then we have integrated for the time they have asked. They are asking for infinite time. So we have integrated it from 0 to infinite. And then we have gotten the power, sorry, energy. Then they're also asking what is the current at steady state. One thing, whenever it is DC, inductor will become short circuit at t tending to infinite and capacitor will become open circuit. So if it is short circuit, then what happens? This resistor will be bypassed by this short circuit. So 2 volt by 12 volt is the current, and that is what we have calculated. And then they're also asking what is the power supplied by the source. Power supplied by the source is nothing but the current it is supplied into the this voltage, which is what gives us the power. Then we have solved another problem which looks very complicated, but again they are saying very long time, which means t is tending to infinite. So capacitor will be open and inductor will be short circuited, and this is the final circuit. Now it's just a resistor as well as voltage and current source circuit. And based on what we have learned in week one, mesh analysis and nodal analysis, using that we have calculated VC1 and VC2. And the last question is again about the time required for the capacitor to reach 1 volt. So first we have to get capacitor voltage as a function of time. For that, we have applied mesh analysis. We got the differential equation. We have integrated it. And then we got the capacitor voltage as a function of time. And then we have seen that capacitor voltage should reach 1 volt. So we have substituted it and calculated the time, which gives us 193 seconds. And in the last question, we have seen that they are giving I profile and they are asking voltage. And they have initial voltage. So at the beginning of this lecture, we had this equation of the voltage. And here integral term is nothing but area under the curve. And this is initial voltage which they have given. So after substituting it and calculating the area under the curve, we got the voltage, and they're asking at 11th second, right? So they're asking, given V of 0 is minus 59, V of 11 is how much? So they're asking till 11 seconds. So we have to integrate till 11. If they ask till 5, we have to integrate till 5. So keep this in mind. So till what time they're asking, until that time we have to integrate it. Using that, we have got the capacitor voltage. So this week is all about inductors as well as capacitors. Any doubts till this point? Anyone? No doubts? Okay. So week 3 was about solution to linear differential equation with different excitation. So in the last week, we were solving it by classical method. And it's a first order system. What happens if it's a second order? What happens if an nth order? How to solve? So in this week, we have basically discussed about how to solve an linear differential equation using some guidelines, because any RLC network will be converted into linear differential equation, and how to solve for the time domain expression. So we have started with the first order differential equation and we have basically solved it. And then we have seen that it has two responses. One is the natural response, another one is the forced response. And then we have solved it, and then we got forced response as a function of like a polynomial of derivatives of this forced input. So now the generalized expression is, if this is the equation, one is the natural response, which is a into e to the power minus at, and another one is the forced response, which is the derivatives of this input, summation of all the derivatives with some coefficients. And we have seen that there will be an exception if x of t is e to the power minus at. In that case, this will be the output. And we have seen first we have to write the generalized solution, and then first we have to obtain the forced response constants by substituting y of t in the LDE. For getting this A, you have to use the initial condition. So using the same guidelines, we have solved multiple problems. So let me just briefly describe what we have done. So in this problem, first we have written the differential equation solution, generalized solution. Then we have substituted back it in the linear differential equation to get K0 and K1. Once we got that, we have used the initial condition to calculate A. So now this is the overall solution for this linear differential equation. Now we have solved another such problem. So I'm skipping this part. Then we have gone to second order differential equation. So now that we have entered second order differential equation, forced response remains same, but natural response will have two equations. I mean, two terms, because there are two solutions to these equations. If M1 is not equal to M2, you will get this expression. If M1 equal to M2, you will get this expression. If M1 and M2 are complex conjugates, you will get the same expression as the first one, original one. But here A1 and A2 will be complex conjugates because M1 and M2 are complex conjugates. Here A1 and A2 are real and M1 and M2 are also real. So once we get this, the method remains same. First, write the generalized expression, solve for forced response by substituting this in the original equation, and use initial conditions to solve for A1 as well as A2. And if it is nth order, then also first you have to solve for this n equations, I mean, n roots. If roots are distinct, then this will be the natural response. Forced response remains the same. And if two are equal, then we'll have this. If three are equal, then we'll have this quadratic term, and rest remains same. Now, then we have solved a couple of problems. In the first problem, they're asking current and voltage. So for any problem, what you have to do is first you have to apply KCL, KVL, mesh analysis, nodal analysis, and get the linear differential equation, second order, first order, third order. And then first we have to write the generalized expression. So I have calculated the roots and they're distinct. And then this is the black color is the natural response, orange color is the forced response. Now for calculating K naught, substitute this in the original equation and solve for K naught. I have obtained K naught. Now use initial condition. So there are two unknowns. So I need two initial conditions. So V of 0 is given, I of 0 is also given. So using this, we have solved for A1, A2 and substitute back to get the overall expression. So I got I of t. Now you can calculate whatever V of t or I of t that they are asking in the question. And then we have solved another such problem. This also remains same. First solve for KCL, KVL and obtain a differential equation. This is the first order differential equation we got. So one term for natural response, one term for forced response. Substitute it to get the coefficients of the forced response. Once you get that, use initial condition to get the natural response coefficients. Once you get I of t, solve for whatever they're asking for, and then get the coefficients whatever they're asking. So till week 3, any doubts? Anyone? Any doubts? No. Okay. So week 4 is about mesh and nodal analysis with time varying source. So here what happens? Now the source is sinusoid or cosine. Previously it was constant. Now it is sine. So how we have solved? So we know RL circuit, what will be the voltage relationship, or basically we have applied KVL and then we got the equation. And then we have seen that sine can be written as exponential. Now we know that this is a first order differential equation. It has a natural response. It also has a forced response. So how to get K1 and K2? By substituting this in the original equation. So we have substituted, we have obtained K1 as well as K2. Once you obtain K1 and K2, we have substituted back in this equation and we got forced response, something like this. And then A is something you will get from the initial condition. This is the initial condition. So we have basically solved everything and then we have simplified everything. And then we got IL of t is something like this. But here, if you see, this decays with time, which means at steady state, this term will vanish. Only this term will be obtained. So in this week, we were only dealing about the steady state terms of a time varying source with RLC network. So in this case, this is the steady state, and we have observed that this can be obtained using phasors, and we have learned about phasors. So these are the conventions that we have used in the phasors. Cos omega t plus theta is Vm angle theta. Sin omega t plus theta is Vm theta minus 90 degrees. And using this, we have converted everything into phasors. R remains R, L remains j omega, C remains 1 by j omega c. And then using the phasor, now we have solved this simple circuit in just 2-3 steps, and we got the same expression which we have obtained by solving a lot of equations using the differential equation solution based approach. Now that we have seen that this approach is simpler, we have started solving problems using this. So first we have to convert everything into phasor. Once we convert everything into phasor, it becomes normal RLC circuit, like a DC equivalent circuit. So we just have to consider it as a basic impedance, and then we have to solve for currents, whatever voltages that they are asking. So basic idea is to convert everything into phasor and then solve it like how we solve a resistor network. And then we have also learned about complex power, which consists of active power as well as reactive power. Units are very important. Complex power units is volt ampere. Active power unit is watt. Reactive power unit is volt ampere reactive. So we have solved another problem where they are asking the complex power, and complex power is V into I star. So once we have this expression, we got that active power is 400 and reactive power is 0. So that's what they are asking in the question. And then we have solved another problem. Here also they have given phasors directly and they're asking what are the currents. So we have applied KCL because this voltage is unknown and these currents are also unknown. These voltages are known. So we have applied KCL at that node and then first we have calculated V bar, which is this voltage. Then we have individually calculated I1 angle theta, I2 angle theta, as well as I3 angle theta. And then we got these values. In the next problem, it's again a RLC network and they have given two sources. So what we could do is we could apply superposition theorem. So excluding this current source means it is open circuit. Now this is the circuit. Using phasor, we got one voltage VC1, and using current source, the voltage source will become short. So the equivalent circuit remains this. And then we have applied the phasor. Using phasor, we have calculated VC2, and then my VC is nothing but VC1 plus VC2. And then that's what they were asking because it has two terms. They are asking AB as well as theta and phi. And whenever you solve these problems, kindly keep this thing in mind. They're saying theta should be in this range, phi should be in this range. So you have to accordingly adjust so that theta and phi will fall in this range. So this is very important thing that we have seen in the assignments. Your answer might be correct, but given this condition, your answer could be wrong. So you just have to transform it into a different angle, and then maybe sine becomes cosine, cos becomes sine, something like that. And you have to ensure that theta and phi is well within this range. Then only your answer will be correct. And else sometimes it could be wrong as well. So any doubts till week 4? Any doubts? So coming to week 5 was about self and mutual inductance of a coil. So there was some doubt in the week 4 assignment. And again, if you see, it is just same as what we have discussed just now. But if you see here, they have mentioned theta range. So whatever you have to do, you have to convert it into some different format because originally we have 100t plus 3 pi by 2, 270 degrees. But they have asked, please ensure this. So I have to convert it into different form and ensuring that it is cos. So now I got a minus sign here. So the answer was different. So kindly be careful with this terminology as well as terms. So if they have given any such range, you have to ensure that theta and phi are well within this range. Now we have come to self and mutual inductance. First, we have learned the dot convention using Lenz law. Why this dot convention is needed, so that we'll know if the current is entering here, current is leaving here, or if both the currents are entering, how the voltage polarity will be looking like. So once the sense of this winding is known, dot convention is known. But every time we cannot give this diagram and then find out the dot convention. So that's why we in the circuit dot convention is directly given so that we can ignore or we can skip writing or drawing this entire big diagram and we can directly write the voltage equations. So there are two cases that we have considered. One, the current is entering both the polarities. In that case, we have seen that the mutual inductance polarity will be same as the self-inductance. If the current is entering one dot and the current is leaving another dot, then the mutual inductance term will be exactly opposite of the self-inductance. So always first draw the self-inductance term, then depending upon case 1 and case 2, you can draw the mutual inductance. For every question, first you draw these voltage sources, then only you start solving it. And then we have solved a couple of problems. In the first problem, this is shorted. So current is entering the dots in both the cases. So first I have drawn self-inductance term, then I have added the mutual inductance term, and then we apply KCL, KVL normally, and then we solve for it. And then we have solved assignment 5. So here there are 3 mutual inductance. So we'll get 3 terms, 3 terms, 3 terms, total 9 terms. So take your time. Don't make any mistake. I have made sure I am using the same color so that you can correlate which term is coming for what. So first I have drawn self-inductance for all these 3, and then I have checked between 1 and 2, 2 and 3, and 3 and 1. Maybe if you could fall in case 1, you could fall under case 2. So if it is case 1, the polarity will remain same as the self-inductance. If it is case 2, then the polarity will be opposite of the self-inductance. And once you draw then 90% of the work is done. You just have to apply KVL and then calculate. But if you make any mistake over here, your answer will be wrong. So take your time, draw the circuit properly, make sure all the polarities and notations as well as the term value, voltage value is correct. Once this is correct, then it's just a matter of two, three equations. You just have to solve for current or voltage, whatever they're asking. But if you make any mistake here, then things will go wrong. Similarly, here we have one mutual inductance, here also one mutual inductance. So here, if you see, it is falling under case 2. Here also it is falling under case 2. So first I have drawn self-inductance, then mutual inductance will be opposite. Mutual inductance will be opposite. So once you do this, I have to apply KVL here, KVL here, KVL here. Then we have solved for I1, I2, and I3. So the entire difficulty will be in drawing this diagram. So this is very crucial. So we have spent enough time. If you have any doubts, you can always go through the lectures. And also this notes is also uploaded, so you can use these notes as well. So this another problem where this is shorted, they are asking what is the effective inductance seen by this source. So we have seen that this falls under case 2. We have drawn it, and then we have calculated the voltage by these net current. So basically we have to find this current I1, and then I have solved for I1, and then the impedance seen by the source is V1 by I1. So this is the overall impedance. So basically, if you solve all the problems that we have discussed, then you will be able to score good marks in the final exam. Also, most of the questions will be of the same format or same model as in the assignment. It will not be just same problem and then values will be changed. Maybe they will slightly change here and there. Say if they're asking Thevenin's theorem in the assignment, they might ask Norton's theorem. Voltage source will be replaced by current source, but the overall concept and you can expect similar type of problems, but not exactly the same set of problems. So this completes week 5. Any doubts before we go to week 6? Okay, no doubts. So week 6 is about circuit analysis using Laplace transform. So the question is, why do we need Laplace transform? We have discussed that if we are solving using LDE, time domain, then it is very complex, but you will get transient as well as steady state terms. If you are using phasors, which is frequency domain, then you will get only steady state expression, although the it becomes easy. So this is lengthy, this is easy, but this has both the information, but it is lengthy. This has only steady state information, but it is easy. So I want to take the advantage of both of this. I want the entire solution, but I want a easier approach. So for that, we use Laplace transform because it converts the differential equations into algebraic equation, then it becomes simpler to solve. And it has the information of transient and steady state. And all the mesh analysis, nodal analysis, everything can be applied easily. So we have first discussed what is a Laplace transform, and then we have seen what are the standard expressions that you need to remember to simplify or to make your life easy. And whenever we are dealing with Laplace transform, Fourier transform, these are the standard results that you have to remember. Because this course does not include Fourier transform, only Laplace transform, I have listed down all the expressions or the results that will be used or that will be helpful and you need to remember. So try to remember all these equations. And then RLC in S domain will be R, SL as well as 1 by SC. And we have seen if they have initial condition, it will have one initial condition term, and here also it will have one initial condition term. So what you have to do, see, this is the same problem that we have solved assignment 5. So I was just discussing, I think someone has asked out. Then for solving any problem, first you have to convert everything into S domain. So that is what I have done. Then you solve in S domain and get everything in S domain, then apply reverse Laplace transform or inverse Laplace transform to get everything in the time domain. So you have to be careful with the partial fractions as well as these results that we have discussed. So you have to be thorough with the partial fractions, not make any mistakes. Also, you should be thorough with the like the results that I have shown in this like document. And we have solved another problem. First, what we have done, we have converted everything into S domain. Then we have applied KVL, KCL, and then we got I1 as well as I2 in terms of S domain. Then we have taken this back into time domain using inverse Laplace transform. And once we have converted this, then you check whether everything again is matching or not. These constants are greater than 0. This is being obeyed or not. If not, then you have to slightly change. And then similarly, we have calculated I2 and then we have converted it back. So once we converted it back, I think there is some issue because it is not fitting into what they have asked. So we have slightly tweaked into a different value so that now it is in the form that they are asking in the question. And also these constants are also fitting in the range that they have mentioned. So you have to be very careful, else you will lose your marks. And then we have seen, so that's why I have highlighted again, all this constant will be positive and all these things will be within this minus pi to pi. So if it is not, then your answer will be wrong. So you have to be very careful. So this completes our week 6. Before we go into week 7, any further queries? So this is basically summary so that if you have any queries or if you miss anything or if any concept is not clear, whenever I am discussing, you can ask. So week 7 is about network theorems. So this is some easier week. So I'll go a little bit fast. So we have discussed about substitution theorem where resistance can be converted into voltage source or a current source. Then we have seen Thevenin's theorem where any linear network will be can be replaced by a voltage source, which is Thevenin voltage, as well as the impedance, series impedance, Z Thevenin. So for calculating Thevenin voltage, you keep all the sources and then find the open circuit voltage. For Z Thevenin, open circuit the current source, short circuit the voltage source, and then find the impedance seen from this pole. Norton's theorem is slightly same as the Thevenin's theorem. Here, we are replacing the linear network with a current source in parallel with the impedance. Impedance remains same, Thevenin impedance. Norton current, how to do? This impedance will be short circuited and then we'll find the short circuit current, which is the Norton current. I'm audible, right? Hello, anyone confirm? Hello, I'm audible, right? Yes, okay. Then we have discussed about compensation theorem, where if some term Z is replaced by delta Z and the current through this is I plus delta I, how to calculate delta I. So this is the uh, net circuit, like equivalent circuit where sources are not there. And this is replaced by this and the current is delta I. Because here we have so many sources, here we don't have any sources. So all this network can be simplified to a simple resistance and it can be easily solved. And we have also seen. And then there is Telegan's theorem, where if two networks have the same graph, then this will be valid. And then we have also seen reciprocity theorem. If the network is reciprocal, then the ratio of the response to excitation remains same, even if we interchange the response and excitation. So this is the excitation and this is the response, and we have obtained this equation. Then we have solved a couple of problems. First, we have to find out under which case it falls. So this falls under Telegraph theorem. So we have used Telegraph theorem and we have solved. So now we have learned the Laplace transform. So we can deal everything in Laplace transform and we can apply inverse Laplace transform. And now that you know, you can always use Laplace transform because it simplifies a lot of things and it simplifies the calculation, also saves a lot of time. And here they have changed resistance. So we have seen that it is compensation theorem. So we have used the equivalent circuit to solve for delta I. And then we have calculated delta I. And then we have calculated the actual current, which is I1 plus delta I1, I2 plus delta I2, I3 plus delta I3. And then the circuit is something similar from our earlier week. So this has nothing to do with this week actually. So it is like a bonus where you have to apply KCL and then you have to solve for the currents. Then we have solved another question where they're asking the Thevenin equivalent circuit. So we have to calculate ZTH as well as VTH. So for calculating VTH, it's an open circuit voltage. So which is what we have done using the S domain. And ZTH is by shorting this, what is the open circuit voltage that you have. See, I think they have already given VTH and ITH. They're asking ZTH. So you know ZTH is nothing but VTH by ITH. So we have done that and then we have calculated everything. So Norton and Thevenin are more or less related. VTH is nothing but ZTH into I Norton. So if you know this, then you can transfer Thevenin equivalent into Norton equivalent and vice versa. So this week we have discussed about various network theorems and also solved a couple of problems on this network theorems. So any queries until week 7? Okay. If no, then we can go to graph theory. Week 8. So week 8 is about graph theory applied to network analysis. So we here this week is very crucial. We have learned a lot of things. Mainly the nomenclature is very, very important. So we have started with graph theory. Why do we need graph theory? Because when the circuit complexity increases, the number of equations increases, and you cannot solve by yourself. You need a computer to do. But for a computer to do, it has to be in a matrix equation like ax equal to b or ax equal to 0. So you have to have a systematic way to write the equations. So for that, we have learned about graph. So any circuit can be converted into graph. So first we have seen graph of the network, then directed graph of the network, then we have seen simplified directed graph. So here we'll write the direction of the current as well as the nodes from which we can get the element voltage as well as the element current information. So then we have seen about tree as well as code tree. I'll not explain in detail. I'll just go surface level. So we have seen what is a tree, what is a code tree. From a given network, we can have a tree, and whatever is not there in the tree, that forms code tree. And elements of the tree are called twigs, and the elements of code tree are called links. And then we have seen first graph theory and nodal method. And then we have applied KCL at 3 nodes, and then we got the equation, and then we have written it in this format. And then we got A matrix as well as IE as well as this zero matrix, and we have seen what is the size of this matrix, and we call this as a reduced incidence matrix. So if they're asking for reduced incidence matrix, they're asking for A basically. Then we have solved one problem quickly using that, and week is very, very easy. If I have to be honest, if you know the concept very clearly, then you will be able to do without any mistakes. And this entire week is all ones and zeros. So if you make any mistake, you'll lose marks. So you have to be very, very careful while dealing with this. And then any circuit they have given, they're asking A. So you have to apply KCL, and once you apply KCL, you will get this A matrix, and you just have to enter these values without making any mistake. Then we have seen a loop method where we have discussed about fundamental loop. What is fundamental loop? If any link is added to the tree, it forms a loop, then it is called fundamental loop. So the number of fundamental loops is equal to number of links, and then we have to traverse through the loop in the opposite direction of the current in the link. So if this is the direction of the current, we have to go in the opposite direction. Uh, that is very, very important. So you have to keep this in mind. And then we have applied KVL, and we got this. And one way to check whether your matrix is correct or wrong is you will get an identity matrix for the links. 4, 5, 6 are the links. So we'll get an identity matrix. And this matrix B is also called as fundamental tie-set matrix. So sometimes they'll ask what is the fundamental tie-set matrix, and they'll not ask what is B. So you have to remember the names and understand it. So in this, we have 2 links only. So we'll get 2 equations. So that's why 2 rows, and they're asking fundamental tie-set matrix or loop matrix, which is B. So we have applied KVL in this, and we have traversed in the opposite direction of the link. So that's why here we are going anti-clockwise, here we are going clockwise, which is the opposite direction of 6 and 7 respectively. And we have applied KVL, and we got this matrix. And just to ensure, I have checked whether I have identity matrix or not. If you are not getting identity matrix, it's a sign that you have made a mistake. So you have to cross check. Then we have also seen cut set method. What is cut set? Any line that cuts the graph into 2 parts. What is fundamental cut set? What is fundamental cut set? It's if the cut set cuts one twig, then it is called fundamental cut set. So how many fundamental cut set will have? Equal to number of twigs. So once we have the fundamental cut set, you have to apply KCL on that side where the current is leaving the cut set. And once current is leaving the cut set, it is considered positive. Current entering the cut set, it is negative. So you have to consider that side of the cut set where the twig current is leaving the cut set. So it will have a positive term. So once we apply KCL on that side, then you will get fundamental cut set matrix. And here also, what is the way to check whether you have done everything right or wrong? The identity matrix. Here you will get identity matrix for the twigs 1, 2, 3. So once you get identity matrix, then you have not made any mistake. But if you don't get, then you have made a mistake. You can cross check again before you enter your answer. And this is called fundamental cut set matrix or Q matrix. Then we have solved again another problem quickly. Here 3 twigs are there, so we'll get 3 rows. And we have considered that side of the cut set where the twig current is leaving. So twigs are 1, 2, 3. So here it is leaving, here it is leaving, here it is leaving. So that's why I have highlighted the region also, just so that you'll know which region we are considering. And I got an identity matrix, which ensures that I have done whatever I have done, it is correct. So any doubt till week 8 before we go to week 9?
No, sir.
So week 9 was about dependent sources, and this is also very easy week. just basically you're applying KCL and KVL, but instead of independent sources, we have dependent sources. What are dependent sources? Their value, current value or voltage value is dependent on another current or another voltage. So basically, if you consider mutually coupled, we have seen this voltage is dependent on some other current, right? So this is a dependent source. Similarly, this voltage value is dependent on some current. So basically, these are dependent sources. And another dependent source we will get is BJT, but BJT or MOSFET, but that may or may not be covered in your curriculum till now. We'll learn it in the future. So that's also one dependent source. They're called current dependent current source or voltage dependent current source. BJT is current dependent current source. MOSFET is voltage dependent current source. Then we have solved a couple of problems. And if you see everything remains same, you just have to use this term in the KVL and then get two equations, two unknowns, depending upon how many unknowns are there, and you have to solve. And this week is also very simple if you do not make any mistake. So we have seen this is independent voltage source, this is dependent current source. So apply KCL, KVL without making any mistake, get the equations and solve for the unknowns. And if they are asking power supplied, we have already discussed the notations for what is the current supplied or delivered. So sometimes they'll ask whether it is supplying or not, whether it is delivering or not. So you have to get this understanding from the voltage as well as the current polarity, whether it is supplying or whether it is consuming. Say if it is consuming and they're asking how much it is supplying, then you will put a minus sign. Just like uh, I have taken one example. Say I have taken 1,000 rupees from you. I owe you 1,000 or you owe me minus 1,000. So basically we are asking in a different way. So that I hope you understand that terminology and everything. If you have any query regarding that, you can stop. And then we have solved another problem where they're asking currents and voltages. So if you see, this is a current dependent on voltage. So that's why they have 8 more because the dimension should be current. And this is a voltage source dependent on current. So that's why it is kind of multiplied by a constant, which has a dimension of resistance. That is what is actually basically happening here. Dimension should also be correct. Then we have applied KCL, KVL and solved for unknowns and everything. Here I have also given the convention. Here it is delivering. This is also delivering. Here it is absorbing or consuming. This is also absorbing or consuming. So if you have any queries, you can always come back here and check whether your concept is clear or not. Then we have solved for power delivered, power consumed. And then towards that, we have solved for another question where they're asking Thevenin voltage. So open circuit voltage, we have to calculate Thevenin. So basically we have to solve for this. And then for ZTH, I have not directly calculated ZTH. Instead, I have calculated Norton current because it makes my life simpler. So I have shorted this and calculated Norton current. And VThevenin by Norton current is my Thevenin impedance. So that's how we have solved. And I also recommend you to solve for Norton current rather than solving impedance. Finding Norton current would be easy rather than finding the equivalent impedance. So always calculate Thevenin voltage, Norton current. From there, you will get the Thevenin impedance from Norton impedance. So any queries till week 9?
No,
Okay.
sir.
If you don't have any queries, then we'll quickly move to week 10. In week 10, we have discussed about the two-port networks, but someone has a query. So this is a very interesting thing. So here we are getting I Norton equals to 0 and R Thevenin is not 0. Because I Norton is 0, you will get V Thevenin equals to 0. So now they're asking R Thevenin, right? But R Thevenin is not infinite. Even if R Thevenin is finite value, because I Norton is 0, V Thevenin will also be 0. So in that case, how to calculate R Thevenin? I have connected a voltage source VT and assuming that it supplies IT. So all the dependent sources has to be removed. And sorry, all the independent sources has to be removed. Means independent voltage source will be short circuited, independent current source will be open circuited, but dependent sources will remain the same. And now I have to solve for VT by IT, which is my RTH. So this is one very important problem and kindly take a note of this. Then in two-port network, this is the convention that we have been following. And I have also asked you to remember this because this is the voltage polarity and this is the current. Currents are entering in both the ports. This can be input, this can be output, or this can be input and this can be output as well. So we have discussed about 4 parameters. One is the short circuit admittance parameters. Then another is the open circuit impedance parameters. Then we have hybrid parameters. Then we have ABCD parameters. So in the case of Y parameters, voltage is the input, current is the output. In the case of Z parameters, current is the input, voltage is the output, and Y is Z inverse. And in the hybrid parameters, it is hybrid. I1 and V2 are the input, V1 and I2 are the output. And if you see, this has dimension of resistance, this has dimension of conductance, this is dimensionless, this is dimensionless, based on whether it is multiplied by current or voltage. And then we have also discussed about ABCD parameters. Here, V1 and I1 are the input, V2 and minus I2 are the output, because if it's a load, then current direction will be minus I2. And here also we have ABCD parameters. A is dimensionless, B is ohm, C is mho, and D is dimensionless. There is less than a minute, so this meeting might end. If this meeting ends, kindly join back so that we can also summarize week 11 and week 12. And then we have seen for reciprocal network, this is the conditions, and symmetric network, these are the conditions. We have not gone into the details of the derivation because we had limited time. So I have just given the result, and you can remember this result. And if this satisfies, it is reciprocal. If this satisfied, it is symmetric. Once again, this meeting might end. Kindly join back if it ends. Then we have solved about few problems. So first problem, they are asking Z parameters. So this Y we have converted into delta, and first we have simplified the circuit, then we have started solving. So we know how to solve for these parameters, either I2 equals to 0. First put I2 equals to 0 and then solve for V1, V2. Then put I1 equals to 0. And then solve for V1, V2, and then from there you will get Z parameters. And they're asking whether it is reciprocal or symmetric. Based on those conditions, we have checked whether it is reciprocal or symmetric. And then in another question also, they are asking hybrid parameters. We know. So first put I1 equals to 0, solve for V1, I2, then put V2 equals to 0, and then solve for V1, I2. So these are all math and circuit solving. And if you do not make any mistakes, here also things are very clear and you can easily score marks. And then they are saying this, they are considering into a single port network. So ABCD parameters will be multiplied. So we have done matrix multiplication and then got. So now they are asking what is the Thevenin voltage. So for Thevenin voltage, we know that all the currents will be 0 and I3 will be, sorry, not this I3 will be 0 because it is open circuit. Then we have substituted that and got Thevenin voltage. And for Norton current, this will be shorted, which means V3 is 0, and then we have substituted and we got Norton current. If we know this, then we also know the Thevenin impedance. That's how we got. So all these problems are very interesting, and they are not just from one concept. They are from two concepts. One is two-port network as well as Thevenin and Norton, which is the circuit theorems. So you should have a thorough understanding on all these aspects, and then you can get the understanding of how to solve these problems. And then here also there is another problem. They're asking Z parameters, and we have already discussed about Z parameters, how to solve. So we'll not discuss this problem because it is same. I1 equals to 0, calculate V1, V2. I2 equals to 0, calculate V1 and V2. And this is not semi-proper, nor it is reciprocal. So two-port parameters are all dependent on these four parameters. Once you know the definition, then you just have to plug in which one is 0 and then solve for the other parameters. And week 11 is also continuation of two-port network, where we have discussed about series combination, parallel combination, as well as cascaded combination. In the case of series combination, we know that the impedance matrix of the series connected will be summation of impedance matrices, whereas in the case of parallel combination, the admittance matrix of the parallel connection will be summation of the admittance matrices. Whereas if it is cascaded, the ABCD matrix of the cascaded will be product of the ABCD matrices. Then we have solved for a few problems, although the problems are not exactly directly dependent on what all three results that we have discussed over here. But we have seen that they're kindly, not kindly, they are slightly twisted and not exactly two-port network. So they have given two-port network of this, and they are connecting something here. So whenever they have given two-port information, first draw the equation, and then you know V1 and I1 in terms of V1 and R, and V2 and L. So write what all equations you have, then substitute it, and then you solve. So first, if you are confused, first put down all the equations that you can write. Then you looking at the equations, you will get some idea. But if you look at the circuit, you will not get idea. So if you are confused anywhere, first write down all the equations that you can write from the circuit. Then you see how many equations are there, how many unknowns are there, whether you can solve or not. Sometimes looking at the circuit will not give an idea, but putting down the equations on the paper will give you. Then this is another question. They are asking some parameters. So you know Z parameters, how to calculate. I1 equal to 0, I2 equal to 0, same old story. And you have to solve to get. Once you get Z parameters, Y parameters is just inverse of that. And here we have seen four other things. One is the open circuit voltage gain, which means port 2 is open circuited, means I2 is 0, Then what is V2 by V1? We have solved. And we didn't actually solve the again center circuit again. From these equations only, we have obtained all this. Here they are saying port 2 is short circuited, which means V2 is 0. So I have substituted V2 equal to 0. Then I have calculated minus I2 by 1. Then the resistance seen from port 1 when 16 ohm is connected. If 16 ohm is connected there, V2 is minus 16 I2. So I have to solve for V1 by 1. So I have solved for V1 by 1. I could again solve the circuit again, but that is basically waste of time. So we have to get to the answer in the shortest possible path in an exam, because that will save our time. Also, we can spend the time in some problem which we don't know, because some problem we are not getting idea how to solve. Then you have to spend some time. So you have to take some time from the problems where you know the concept. So you try to solve quickly, also solve correctly, and get to the answer as quick as possible. So you can save this time and use it somewhere where you need more time. So exam is all about time management, making the right choice at the right time, and solving everything without making mistakes, or with less number of mistakes. And then what is the resistance seen from port 2 when 16 ohm is connected? So 16 ohm is connected means V1 is minus 16 I1. We are solving for V2 by I2. And then this is another important equation. So they have given two-port network for the inside one. They're asking the two-port network of the outside one. So you don't know. First, you write down V1 and V2 dash in terms of I1 and I1 dash and I2 dash. And also I can write V1 in terms of I1 dash and V1 dash. So basically I have put down the equations that I know. Then I have seen that one of these equation I can substitute in the other to get the two-port or the Z parameters of the outer box. And then we got this uh, Z parameters of the outer box given the Z parameters of the inner box. So all these are a little bit tricky problems, but they are very simple. Once you put down the equations, you will get the idea, and I'm very pretty sure about it. And here they're asking about Y parameters. You know how to get the Y parameters. And if they're connected in parallel, you know the Y parameter is nothing but summation of these. So as these are same, so the Y parameters of this is nothing but twice of this individual Y parameters. So this completes our week 11, which is the series parallel as well as the cascaded combination. Now we'll go to week 12, which is the ideal op-amp circuits. And this week is also very simple. It relies on only few things, which I'll explain now. So we have seen how an op-amp looks like and what is the practical circuit or practical IC looks like. And then we have seen the ideal, non-ideal op-amp characteristics, which has some linear region as well as saturation region. And this is the circuit. If it is an ideal op-amp, input resistance will be infinite. So input current is 0. Output resistance will be 0 and gain will be infinite. So the IV characteristics will look something like this. Now it has become two regions from three regions because the linear region vanishes. And we have seen because A is infinite, V2 will be V1 and it is virtual short. So all the problems we have solved based on three things. One is virtual short. Another thing is the input current is 0. And then what is the third thing? Third thing is KCL or KVL. So three things we have used. One is the virtual short. Second thing is the input current is 0. Third thing is the KCL or KVL. And we have discussed some very famous circuits which will be helpful throughout our life if we work on circuit-based things. One is the inverting amplifier where the gain is negative and the value can be less than 1 magnitude or more than 1. And then we have discussed about non-inverting amplifier. The gain is always greater than or equal to 1 and the gain is positive. And then we have discussed about the differential amplifier where the gain is positive and it can be less than 1 or also greater than 1. And then we have also seen a buffer circuit where output is equals to input. Then we have solved a wide range of problems, but all the problems I have used the same three concepts. Input current is 0 and V plus V1 equals to V2, which is the short circuit, not short circuit, virtual ground of the positive terminal as well as the negative terminal of the op-amp, and then applying KCL. So all the problems has the same set of things. So we have solved wide range of problems and wide type of problems, multiple type of problems, but everywhere I have applied the same thing. So here is another problem where this is ground. So this becomes ground. So once this becomes ground, here current entering is 0. So I have used two rules already. What is the third rule? KCL. So current entering equals to current leaving and then solve for V0. So op-amp based circuits are very simple. You just have to keep in mind these three things. One is virtual short. So the non-inverting terminal and inverting terminal have the same potential and the current entering the op-amp is 0 and then KCL. So the three equations, the three things I have used to solve wide range of problems. All the problems are almost the same. Only they're a little bit different, but don't be tensed or worried looking at the circuit. First, you have to use whatever we know. So, say some circuit is there, some which I think we'll go to the this complicated circuit is there. So it looks complicated, but I know one thing: current here is zero, current here is zero. So I'll break down the circuit into small chunks and parts. So now these two currents is zero. Also, I know whatever is this voltage will be this voltage. So first I have to find this voltage. So this current is zero. Now this becomes a resistor divider, or you can apply KCL here. So I have solved for the this voltage. I know this is one voltage. So first we have used one guideline, which is current entering is zero. And then we have solved for this voltage, means this voltage is same. So we have used the second guideline, which is virtual short. Both the voltages will be same. Now we have used the third guideline, which is KCL. And you also have to know where to apply KCL. I have to apply KCL here because I need some equation dependent on V0. Because no current flows here, current in this direction is same as this, which is 2 minus 1 by 1K is equals to 1 minus V0 by 4K. And we got V0 as minus 3 volts. So all the problems are basically using the same thing, same knowledge. So this completes our week 12. If you have any queries, we can ask, else we'll wind this session here.
Sir,
Yes.
can we assume at a 0 volt node the current is leaving, sir?
Sorry.
At the 0 volt node current is leaving, can we assume for KCL
Where?
equation?
In this question.
For any question at zero, if a node has a 0 volt, can we assume current is leaving for writing a KVL equation?
Yes. See, if no convention is mentioned in the question, you are free to choose your own convention. Unless if it is two-port network, where I1, I2, V1, V2 convention is already given. So if the convention is not mentioned by me, saying that this is the convention you have to follow throughout the semester, and say some circuit is given, and in the question also they have not given the current direction, you are free to choose the current direction. But once you choose the current direction, you have to stick to that convention and write all the KVL, KCL with respect to that current equation. Else you will get a wrong answer. So consider a convention. If it is not given, stick to that convention, solve the entire circuit using that convention, and then get the voltages and currents.
Yes, sir. So for solving the questions in exam, uh, should we redraw the circuit or
For
if
solving
we
in the
do
exam, sorry.
should we redraw the circuit for calculating in
Yes.
exams, or just by seeing the circuit we can solve?
No. Always don't try to write down the equation directly. You do it slowly. Like you redraw the circuit on your notes, and then looking at the circuit, you draw the equation. Don't look at the screen and then draw the equation. Then you might make mistakes. So this is something I follow. I try to redraw however big the question is. I'll try to draw the equation first correctly in my notes. So now I look into my notes and then I write the equation. So I don't have to look at the screen and look at down. So in that case, I have made mistakes. So I try to minimize those mistakes. So I'll always draw the circuit. So every time if you see, I'll try to draw the circuit. And then from the circuit, my own circuit, I'll try to write down the equation. So you can also do the same.
So which week will we have more questions in exams?
That I cannot say, because all the weeks are there for syllabus. So whoever is setting the paper, it is up to them. I am not setting the paper. I am helping you to understand all these weeks. So you should be thorough with all the weeks, because every week is interlinked. If you see two-port network is connected with the Laplace, two-port network can be connected with the uh, circuit theorem, network theorems. Two-port network can be connected to mesh analysis, nodal analysis. So all are interlinked. So try to go through all the weeks. Maybe you are weak in some week, but don't ignore any week. I have tried to make it as simplified as possible to make you understand. So go through all the weeks. I know some weeks might be tougher, some weeks could be easier, but go through all the weeks, put in same effort in all the weeks, and with that, it will be helpful. Say sometimes I feel like graph theory is too difficult. Let me skip it. But maybe the question that is given in the question in the exam might be very simple than the mesh analysis that is given. I think that mesh analysis is easy than graph theory, but the question from the graph theory could be very, very easy compared to the question that is given in mesh analysis. So you cannot predict anything. We have to treat all the concepts equally. You should not show any bias. So prepare for all the weeks with same effort, then you will do better.
Sir, can we have the notes that you discussed? So in the PDF.
Yes, yes, all the notes are uploaded into my drive. I have shared the link in the drive. So yeah, please refer to that. Maybe I'll mention the link again.
Can you please in the chat, sir, so that we can.
Yes, yes, yes. I'm just going to give you 1 minute. So any other queries? We are running out of time. I have to leave it.
No, sir. Technically, everything is fine, sir.
Okay.
Actually, we need to thank you for the help and support from the last 12 weeks.
Thank you.
In the YouTube channel only, sir, or okay, sir, drive access. Okay,
I have put all the necessary links, so you keep this with you, and it will be helpful. You go through them.
Okay, sir.
Yeah. I wish you all the best. Go through the notes, go through the lectures, and please do well. Score as much marks as possible. Yeah, and it's
Thank
been
you, sir. Thank you
really
very
nice interacting with you all. You are very energetic and interactive, and I hope this course will be helpful in your future also. And anytime you can contact me. In my YouTube, I have mentioned my LinkedIn, so we can connect it on LinkedIn, and we can stay in touch.
Yes, sir. Yes.
Okay, then if you don't have any more queries, then I'll wind this session here, and I wish you all the best for your exam. Prepare well, do well, don't make any mistakes.
Sir, can you share the links once again so that I can copy the, sir? Actually, I have.
Okay, I'm just mentioning again. Once you copy, let me know so that.
Yes, sir. Yes, sir.
Have you copied?
I have not received, sir, actually.
I have mentioned
Actually,
in the
I have
chat.
opened in the.
Others are able to see, right? In the chat, I have mentioned links.
Actually, I have. Yes, sir.
Others, can anyone please confirm? Hello, can anyone please confirm if they are able to see the links that I have mentioned in the chat?
Yes, sir. Yes,
Okay.
sir, that are available in the chat.
Okay. So, Chandrasekhar, you have received?
Yes, sir. Yes, sir. Yes, sir.
Okay.
Okay, sir. Thank you, sir. Thank you very much.
Thank you all, and I wish you all the best. Prepare well. Don't make any silly mistakes or calculation mistakes.
Okay, sir. Thank you very much.
Okay. Thank you. And I also wish you all the best in your career ahead. Okay, with that, I'll wind this session here. But you are always free to approach me if you have any queries or regarding anything in your future. We can stay in touch. You can get my LinkedIn link from my YouTube channel. Okay, then see you all. Good night, and I wish you all the best again.
Thank you, sir. Thank you very much.
Thank you.
Good night, sir.